Okay, so now we got it going. All right, so some bookkeeping items. First of all, and I hope you all had a wonderful Thanksgiving and you weren't around anybody, and if you were, hopefully you don't get COVID. So, anyway, on the planetary motion and circular motion test, if the test did not go as well as you had hoped, and you're going to take the other version of that, then email me and I will send that out to you. That just needs to happen like sometime, hopefully early this week. So just let me know if you want to do that. Like I said, the new score will be 60% and the old score will be 40%. So there's that. So on this momentum thing, so we've got kind of this big unit on momentum, and then we've got, which will take us about 8 days to get through, so the test over momentum is going to be kind of middle of next week-ish, something like that. I'll send out the calendar once I get a better feel for how this deal is going to play out. Since we're going to be remote now until at least Christmas, so I got to kind of figure out how this thing is going to work. So if you want me to print out everything for this momentum unit, because there's some assignments, some labs, lecture notes, that type of thing, if you want me to print them out and have a packet for you up in the front office, then email me and let me know. Otherwise, I'm just going to send them out, and I'm assuming that you can print them, okay? So if you actually want hard copies of this stuff, okay, then let me know, okay? One of my sisters has called me because we've got a cousin that's in the hospital, and I need to talk to her right quick, so my apologies, but this is kind of an important family matter. I'll be right back. Sorry about that. Ironically, we have a cousin of our family who is in the hospital with COVID right now and not doing very well, so I had to take that up. Okay. Speaking of testing, so there's been some incidences with some testing irregularities. Let's put it that way. So from now on, and I've got to work out the logistics of this. From now on, if you're taking the test at home, you're going to have your Zoom camera on, and I'm going to watch you take the test, okay? So I didn't think it would be an issue, but it has raised its ugly head, and so we'll deal with that later, but you just all need to be aware from now on, when you all take the test, your Zoom camera is going to be on at all times so that I can watch you take the test, and when the testing time is done, you're done with your test. That's it. You're going to take a picture, you're going to send it in just like if you were in the classroom. So I hate to resort to that, but like I said, there's been some irregularities. Also, I'm going to be sending out the academic integrity policy for the district to remind you all that cheating is not acceptable on any test or any homework. And again, I've never had to deal with that. until this year, so we'll deal with that later. So I'm just warning you in advance right now. Also, with Christmas coming up and trying to raise money for the solar panel, we talked about before, I'm going to be sending out an order form for the solar merch that has like the hoodies and the sweatpants and things like that. So if you want to order some, great. Basically $5, which is about what I get out of each order, will go towards your class fund. So I'll be sending that out. The deadline for that is going to be this coming Friday. I don't necessarily need your money by Friday, but I do need to know what you want to order by Friday. So there's that. Yeah, okay, so those are the big things. All right, so let's talk about momentum. So momentum itself is one of the easier equations that you will see. So, and this is on your equation sheet, oddly enough. So here's your equation. It's mass times velocity, okay? Simple as that. Momentum is equal to mass times velocity. So here's as simple as a momentum problem can possibly get. So let's say that you have a 1 kilogram mass and it's going to be moving at 5 meters per second. Okay, so here's a 1 kilogram mass, 5 meters per second. Okay, so that's just going to be 1 kilogram times 5 meters per second. Now, in terms of units, and you'll see that there's two different options on this, and I don't care which one that you pick. It's a personal preference thing. Both have their advantages. So one option is you can go kilograms meters per second. Now, that isn't force. It's not kilograms meters per second squared. It's kilograms meters per second. So that's an option, okay? And you'll see why this works later on. You can also write that as 5.0 Newton seconds. And the reason that you can write this as Newton seconds instead of, which is going to be the same as kilograms meters per second, because if you look at newtons, well, newtons are kilograms meters per second squared. And if you multiply meters per second squared times seconds, one of the seconds cancel out, and you still get kilograms meters per second. So you can either write it as Newton seconds or kilograms meters per second. I don't care. Just pick one, okay? Doesn't make any difference. Simple as that. Now, here's the other thing. Notice that this is mass times velocity. It is not weight times velocity. So if I have a 1 kilogram mass on Earth that's moving at 5 meters per second, and if I take this thing to the moon, okay, and I make it move at 5 meters per second, it still has the exact same momentum. If I'm on Jupiter, if I'm on Pluto, if I'm in deep, deep space, doesn't make any difference, okay? Because it's mass times velocity. It isn't weight times velocity. So no matter where I am, this is still going to have the same momentum as long as it's moving at 1 meter per second. Boom, there you go. Now, the next question is that, wow, is this thing a vector quantity or a scalar quantity? So, Josh Sproles, do you think, I'm about to make you all turn your cameras on because I just hate teaching to nothing but blank screens. Josh Sproles, do you think momentum is a vector quantity or a scalar quantity? And why?
Scalar.
Nope, try again.
Vector.
Very good, okay? Now, if it's a vector quantity, which it is, Mr. Sproles, what two things does it have?
Direction.
Yep. And what? Rhymes with agnitude.
And
It rhymes with agnitude.
magnitude.
There you go, okay? So it has magnitude and it has direction, okay? So if I'm defining this direction as being positive, and it's moving at positive 5 meters per second, if it moves in the opposite direction, then it's going to be moving with a negative velocity, and it's going to have a negative 5 meters per second. So I could also take 1 kilogram multiply that by negative 5 meters per second, and I would get negative 5 Newton seconds. So because momentum can be positive or negative, right? That means it's a vector quantity. So, which means I can represent it as an arrow. So I could have a momentum vector like this is 5 Newton seconds. I could have one in the opposite direction, which makes it negative 5 Newton seconds. Okay? Simple as that. Now, Caden Dolman. Is it possible for this golf ball, okay, which is really small, and this 1 kilogram mass, which is really massive, to have the same momentum?
Yes.
Correct answer. Why?
I don't exactly know.
Okay, you multiply two things together to get momentum, mass and velocity. So the golf ball has a very small mass. This has a very big mass, right? So what could balance it out?
If the golf ball had like a smaller, or no, if the golf ball had a larger velocity
Ah, there you go.
at the smaller velocities.
And the larger mass was moving slower, right? So you can have two objects that have the same momentum. So momentum, in the terms of the golf ball, could equal a very small mass moving with a high velocity. The 1 kilogram mass, which would have a larger mass, could be moving with a small velocity, okay? So two objects of unequal mass can have the same momentum. It just has to be proportional, okay? So the smaller object could be moving very fast, the larger object could be moving very slow, okay? Now, if you look at this in terms of inertia though, okay? So, Wirtz, what's the only thing that determines inertia? Okay? So is it ever possible for the 1 kilogram mass and the golf ball to ever have the same inertia? No. So here's the whole kicker. Inertia is determined only upon mass. So this golf ball and this 1 kilogram mass can never have the same inertia, but they can have the same momentum. Okay? So that's going to be one of the key things to look at. All right. So, by the way, the test is not going to be 50 problems where you multiply mass times velocity to get momentum, okay? In reality, where this becomes more complicated is if you begin to change your momentum. So here's the deal. So since momentum is mass times velocity, okay? If we're going to change the momentum, the only way that we can change the momentum is if we change the velocity. So unless I explicitly tell you otherwise, you assume that the mass remains constant. So unless you are explicitly told, like it's like a rocket engine, okay? So rocket engines work by expelling large quantities of fuel at a very high velocity, okay? So if it's a rocket engine, you change the mass and you keep the velocity the same. What we're going to deal with is keeping the mass constant, and we're going to change the velocity, okay? Now think this through. So I'm going to throw this thing up in the air, right? So I'm going to throw this golf ball up in the air, okay? So, Suzanne Avery, when I throw this ball up in the air and it comes back down, is the momentum changing?
Yes.
Why? That's right, and we're changing the velocity, it's accelerating, right? So if we're going to change momentum, okay, so a change in momentum is going to be mass times change in velocity, okay? So we're going to keep the mass the same. Now, what you're also going to see is that there's a whole bunch of different ways that we can write this, okay? And as we get into more and more things that are equal, it's imperative that you keep track of what's constant and what is changing. So I can write this, change in momentum is mass times change in velocity. I can write that as mass times v minus v naught, okay? I can also write change in momentum as momentum final minus momentum initial. Now, the reason that we let momentum be represented by the letter P, because number one, it would just get confusing if we had momentum and mass in the same equation because we didn't know which one we're dealing with, okay? The other reason is that the letter P comes from an old concept that used to be known as impetus, okay? So the concept of impetus was that when you push something, you give it like a certain amount of impetus, okay? And when that impetus runs out, the object stops. So the more impetus I give it, the farther it's going to go before it stops. And that kind of makes sense. It was almost like a fuel tank. So if you don't give it much impetus, it doesn't go very far. If you give it a lot of impetus, it goes farther. So that's where that letter P comes from on momentum, is from that old concept of impetus. Now, so here's the deal. So if you look at something simple, okay? So let's say that you've got a car with a mass of 10 kilograms, right? And let's say that it's moving at, 5 meters per second. And we're going to hit the brakes and we're going to make the car come to a stop, okay, where my final velocity is going to be 0. So what you'll also see is that this is going to tie together a whole bunch of things that we've already talked about. So if you go back to Newton's first law of motion, right? Objects in motion remain in motion until an outside force acts upon them, okay? And then that's going to change the velocity. So here's the deal. So anytime, this is what Suzanne equated and saw, was that I'm going to take this car from 5 meters per second to 0. So as soon as I begin to change the velocity, I begin to change the momentum. When I change the momentum, that's going to require an acceleration. To have an acceleration, that's going to require a force. So if I were to just calculate my change in my momentum, so my change in my momentum would be mass times v minus v naught. Now, it is imperative that you keep track of the fact that this is v minus v naught, okay? You just can't look at this and go, oh, it's 5 meters per second and 0. Oh, that's 10 times 5. I got 50, okay? It's not it. You have to look at this in terms of final velocity and initial velocity. So in this situation, that would be 10 kilograms times 0 minus 5 meters per second, which would be negative 50 Newton seconds, okay? So the car is moving along, I hit the brakes, boom, begin to accelerate. Now, you can also look at this in terms of a velocity time graph. Yeah, we're going to go old school on a whole bunch of stuff. So if you look at a velocity time graph, this car is starting at 5 meters per second, and it's going to go to 0 meters per second. So if your velocity time graph is any kind of sloping line, sloping up, sloping down, whatever, if your velocity is changing, guess what? Your momentum is changing. So that's the other way that you can look at this. Oh, okay, right. Here's 5 meters per second. I hit the brakes. I slowed down to 0. I was accelerating. My momentum was changing. So that's the other way that you can look at this. So if your velocity time graph has any kind of slope, that means that your momentum is changing. Now, you can also look at this on a new graph, which is going to be a momentum time graph, okay? So we started up here. If you were to calculate the initial momentum of the car, if I said, okay, hey, your car has a mass of 10 kilograms and it's moving at 5 meters per second. What's the initial momentum of the car? Oh, okay, that's simple. That's 50 Newton seconds, okay? Because I took 5 times 10, I got 50 Newton seconds. So that's the initial momentum of the car. Now, I'm going to hit the brakes, and this thing is going to go to 0. Oh, okay. Right, this thing is going to go to 0 in some amount of time. So let's say there's 0, and let's say for the sake of argument that that took 2 seconds, okay? Just to make up the number. Let's say it took 2 seconds. Now, here's the deal. So, Maddie, you with me?
Yes.
Fantastic. So, you have 2 points on this line. 50 Newton seconds and 0, and then you have 0 and 2 seconds. Even though you're coming off of a Thanksgiving feast, do you have enough information to find the slope of that line?
Yes.
What would the slope of the line be?
Would it be negative 25? No. I don't know.
No, you're good. You're good. You're good. You're good. You're good. Your units are, you haven't said the units yet, but your mathematical answer is right. So, it is going to be negative 25. So here's the deal. So what she did, I'm guessing, is that she took 0 minus 50 Newton seconds, and then divided that by 2 seconds minus 0. Now, here's where the magic happens. This is Newton seconds, and this is going to be in seconds. So the advantage of expressing momentum in terms of Newton seconds is because once you get here, then when you're going to find the slope of this line, the seconds cancel out and you're left with newtons. So the slope of this line is going to be negative 25 newtons. Now, Maddie, one last question, okay? So what does the slope of a momentum time graph give you?
Force.
Beautiful, okay? So the slope of a momentum time graph is going to give you net force, okay? So here's the deal, and this should make sense. So if the car is traveling at a constant velocity, meaning that the momentum isn't changing, this would be a horizontal line at 50, okay? Momentum isn't changing, it's constant momentum, means that there's no net force. Now again, that doesn't mean that there aren't forces acting on the car, okay? So if here's the car, and it's moving at a constant velocity, okay? You have gravity, you have normal, you have force applied, you have force friction, you have all of those forces acting on the system, but you're just not accelerating because all of the forces add up to equal to 0. But if I move that along and then I make it accelerate, then the forces aren't balanced and then my momentum begins to change. Okay, so the slope of a momentum time graph gives you the net force acting on the object. If it's a horizontal line, it means there's no net force, and that means your momentum isn't changing, which means your velocity isn't changing, which means that you're not accelerating. Okay, so all of this kind of needs to fit together as like a big idea. Okay, now, Miss Eiston, you there? Okay, here's my question. Instead of taking 2 seconds to come to a stop, okay, I'm going to make that car stop in 1 second, okay? So I'm going to go from 50 Newton seconds to 0 in 1 second, okay? Now I want you to think very carefully before you answer this, okay? If I go from 50 to 0 in 1 second, okay, listen very carefully to what I'm about to ask you. What does that do to the value of my change in my momentum? Does it increase, decrease, or stay the same? Ms. Eiston? Nope. Nope. It doesn't change, because here's the reason why. Because my final momentum is still 0. My initial momentum is still 50. So my change in my momentum, okay, is still, I'm still going from 5 meters per second to 0, okay? This is just a steeper line because now I'm going in 1 second. So it's still 10 kilograms times 0 minus 50. In terms of change in momentum, it's still 0 minus 50. So my change in my momentum is still the exact same. Okay? My change in my momentum is the exact same. Okay? As long as I still go from 50 to 0, how much time it takes doesn't matter. But here's the kicker. Now when I look at this slope, okay, and this is what I want you to think through, okay? So visualize this. You're driving your car and you hit the brakes, and it takes you 2 seconds to come to a stop. Next situation, you're driving your car, and you hit the brakes because a bunny runs out in the road, and you like bunnies, okay? And you slam on the brakes, and it only takes you 1 second to stop. So in both situations, you're going from 5 meters per second to 0, if you like velocity, or if you like momentum, you're going from 50 to 0. The only difference here is that you're taking 2 seconds, and over here you're taking 1 second, okay? So that's the fundamental difference between the two of them, okay? So here's the deal. This is what I want you to look at. So if you look at the slope of this line, Maddie, we're back to you because you've got the slope thing figured out. So Maddie, on this line, I'm going from 50 to 0 in 1 second. So what's the slope of that line going to be, Maddie?
Negative 50 newtons.
Negative 50 newtons. So Maddie, with the steeper line, what's happened to the amount of force that it takes to stop the car?
It's greater.
Beautiful. Okay? What does it say? All right, Suzanne, we got you back here. Okay. So, here's the deal. So the steeper this line is, the bigger the force is going to be, right? Now, here's the classic example. So here I've got a raw egg. Okay? Now, this is a situation that you all intuitively understand the slope of this line. And you're going, no, we don't. Yes, you do. You all intuitively understand the slope of this line and what it means. Because here's the deal. Let's say, and this is a classic demonstration that I'd love to do in class, but obviously I can't. So I'm going to have to show you footage of when I actually did this in class. But if I threw this to Sproles and said, so Sproles is sitting over here, right? And I throw this raw egg to Sproles and I say, Sproles, I want you to catch it. But obviously I don't want the egg to break, okay? So here's what Sproles would intuitively do. Sproles would intuitively catch this egg and he would cradle it, okay? Now, here's what he's doing, is that the other side of this is that force, and you'll see why this works in just a second, is that force times time also equals change in my momentum. So here's the deal. What Sproles is doing by cradling the egg is that he is increasing the time for the change in momentum to occur, which is going to decrease the force. So if you look at this graph, okay, the Maddie momentum graph, okay, well, this is we'll just call this the MM graph, the Maddie momentum graph. So when Sproles catches that egg and cradles it, he's not trying to decrease, and listen to me very carefully, he cannot change the amount that the momentum changes. Because this egg is going to come in with a certain amount of momentum. And whether he catches it like this, or if he cradles it, it's still going to be the exact same change in momentum because the egg is still going to come to a stop. What he changes is the amount of time. So by increasing the amount of time, Sproles decreases. Now listen to me very carefully. When you increase the time, you decrease the rate of change in the momentum. Okay? So this is like a rate function. Okay? Listen to me very, very carefully. Listen to me very, very carefully. This is a rate function. So when you have, and I always change colors, it's that important. Yes, I'm going to change colors. So the slope of this line is a rate of change in your momentum. So with a more shallow line, the rate of change in your momentum becomes less. Okay? With a steeper line, you have a greater rate of change in momentum. So don't confuse change in momentum with rate of change in momentum. On both of these lines, you're going to have the exact same value of change in the momentum. But by increasing the time, you decrease the rate at which the momentum changes. So this is why you all would intuitively catch that egg and you would cradle it. So the other way that you can look at this, oddly enough, and here's a new graph, right? And this is a force time graph, okay? So here's what's going to happen. When Sproles cradles that egg, okay, he wants to increase the amount of time for this egg to stop. Now, look at what happens with the units. Here I have a force in newtons. Here I have a time in seconds. Okay? So, Ismail, you with me?
Yeah.
Okay. So, if I were to find the area for this graph, okay? All right? If I were to find the area for this graph, what units would I end up in?
Newton seconds.
And what does Newton seconds measure? Close. Throw the word change in there.
Changing momentum.
Change in momentum. So the area, well done Ismail. So the area on a force time graph, right? The area on a force time graph equals change in momentum. Now, keep in mind, this is the net force, okay? This is the net force that's causing an acceleration. So when Sproles catches this egg, he wants to increase the time by doing this to create a certain change in momentum. Now, if Sproles just holds his hands like this and catches it, okay, he doesn't cradle it at all, here's what's going to happen. Then, what's going to happen is that he's going to catch that egg over a smaller amount of time, okay, because he's just going to have his hand like this. So, but with a smaller amount of time, that's going to create more force, which is going to make the egg break. So, in both situations here, it's the same change in the momentum, which is going to be the same thing true of this, okay? So, in this situation, you have 50 Newton seconds going to 0. When it takes 2 seconds, you have more time. That's going to be less force. Over here, if you do it in less time, it's the exact same change in momentum, but it's going to require less time, so that's going to require more force. Now, the other thing about terminology, when you see the word impulse, okay, because this is technically known as the impulse theory. So when you see the word impulse, that means the exact same thing as change in momentum. So if you, on the problems that you're going to have on this assignment, if you're going to have, if I say, hey, what's the impulse? Impulse just means change in the momentum. Okay, now I'm going to disconnect this and I'm going to hook it up to my other computer so that you all can watch this demo that I normally would do in class, okay? So I can't do this myself because I've got to throw a raw egg into a sheet, and I've got to have people to help me with that. So give me a second, I'm going to switch this over to my other computer. Now my sound has been a little sketchy, so we're going to try the sound.
Please miss.
Okay.
We all just eggs for real.
We are not eggs for real.
We are eggs for
We are
real.
not eggs for real. I don't even know what this
We are
means.
eggs for real, that's what it means. We're all just eggs for real.
This is a very random class that I was filming this in, by the way. If you know Max Emerson, he was the one that was filming. Now, here, wait.
There's yolk on this
I think I
blanket.
see a yolk.
There's yolk on the blanket.
Okay. So now,
There's the yolk.
kind of bring that bottom edge up, okay, so that it doesn't. Okay, here we go. All right, just kind of lower, pull it down just a little bit. Top up, there you go. Okay, lower the bottom down a little bit. There we go. Okay, perfect. Okay, so I'm gonna take this, right, we're gonna give it a blanket, right? This is a harsh crowd, by the way. This is a harsh class. Okay. All right. So we got that one, right? Egg and bread. So did I impart an impulse onto the egg?
Yes.
Why?
Change the.
Change the momentum. What did the blanket do?
Pardon the impulse.
It also imparted the impulse, but that impulse made the egg
Slow down.
go down. Which one had the greater impulse? They're the same. Okay? The impulses are the same. Now, we throw it a little faster, and don't let go of it, because if it goes south, it's because you guys dropped the plane. Ready? Okay?
Right, build it.
No, it's just, no. Oh, no. So, who's got the best arm? Now, if you miss, which happened last year,
I remember
Okay.
that. I heard about that.
okay, so a young lad, I was doing it over here on this wall, and had the blanket here. A young lad hit through it, missed, and it hit like right between the door and the floor. It was like an asteroid hit the door. It scattered all the way to the. It was, that was horrible. It was horrible. Okay,
So good.
so you, wherever you want to be,
Carson.
I feel better if you were probably a little closer.
Carson.
Okay?
If you miss, I'll give you $20.
Comfortable that I know you're not gonna miss.
Carson, if you miss, I will give you $20.
Skip it off the desk.
Okay, all right. Oh, yeah, hey, take the curl off if you want, but don't miss.
Yeah, I deserve to see.
This one's for you guys.
Now's a practice.
That's practice. Okay. So let's have full speed.
Hey, Jason, you
Full speed. Okay? That was nice. Okay, so, they didn't break, right?
First, do you break the egg in your hand?
No. But, if I take that same egg though, and drop it from just this height.
Here.
A kid just randomly fell out of the chair.
That was Vonda, for those of you who didn't know.
Okay. So if I take this set, ready? You ready, Vaughn? I don't have to miss it. then if I take that same egg and just drop it from this height, what's gonna happen?
It's gonna break.
Oh.
Okay? Oh, yeah, it broke.
Oh, not the cheek.
Oh,
Oh,
There's a reason you're the closest one to that.
I think I'm getting used to that.
Wait, do
Okay,
we have
so
another
let me
egg
move it
that I
back
can
over to
prove
this.
that wrong with?
Yeah, no. Can I get some?
Okay. Come on. Pick it up, pick it up, pick it up. Oh, don't be this way. There we go. There we go. Okay. So, here's what I want you to see coming out of this, is that what happened with the egg, okay? If you were to look at a momentum time graph, right? So, the momentum time graph would look like this. The egg started at 0. And then when it was thrown, this was when the egg was here, right? So the egg was at rest, so it had no momentum. And then we're going to throw it. So the egg is going to go from 0 to some amount of momentum in a certain amount of time, okay? Now, this is when I'm going to let go of it. And the egg is going to fly through the air, okay? So while it's flying through the air, there's no net force acting on it, so there's no change in the momentum. So this is a relatively flat line, okay, which means your momentum isn't changing. And then boom, it's going to hit the sheet. Now, when it hits the sheet, the idea being is that the sheet increases the amount of time for the change in momentum to occur. Now listen to me. The sheet does not reduce the change in the momentum. The sheet reduces the rate of change in the momentum. So if you miss, okay, if I did this and miss, what happens is that the momentum that the egg at this point hits the wall, which means the change in momentum is going to happen extremely rapidly, okay? So if I hit the wall, it's still the exact same change in the momentum. But what's happening is that that change in momentum is happening very rapidly, and with a rapid change in the momentum, that's more force, the egg shatters. So in both situations, the change in the momentum is the same. Okay, so that's one thing you have to focus on. The change in the momentum is going to be the same. But by increasing the time, you decrease the force. Now, if you get a job working for, you graduate from Mays, you get a job as an engineer working for the safety features on a car. Okay? All right? You're in charge of design. So if you're a safety engineer for a car company, you live and die by this equation, that change in momentum is force times time. The whole idea of safety bumpers, airbags, seat belts, all of that serves to function in one capacity. Every safety feature on your car works off the idea that you want to increase the time to decrease the force for the change in the momentum to occur. Okay? All you're trying to do is flatten out the line on a change in momentum time graph. Okay? That's the whole purpose of this. Now, if you've ever done gymnastics, okay, which I'm guessing some of you have done gymnastics in your life, okay? Hannah Blair, I'm guessing in all your tumbling and cheerleading, okay, you've done gymnastics. And I'm guessing one of the things that they taught you is that when you land, okay, you want to bend your knees. You don't want to land with your knees locked. Because the reason that you bend your knees, and this is a situation that you all, like I said, you all intuitively understand this equation. So, when you look at this change in momentum, force times time, when you land with your knees bent, okay, you're increasing the time for the change in momentum to occur, which means you're decreasing the force, okay? That's what's going to happen. But if you land with your knees locked, okay, what happens there is that if you land with your knees locked, then you shrink the amount of time, which means you increase the force, which means that that's going to hurt a lot. And I know there's footage out there of like people landing like that and their knees like buckle. It literally makes me sick to my stomach to watch it. And so no, I'm not going to show you that footage because it literally grosses me out. It's just horrible to watch. Oh, it's horrible. Okay. Now, here's the other thing to look at. Okay? So in this situation, in everything that we've talked about so far, we've kept the change in the momentum the same, and we've looked at the interaction between force and time. Okay? Now, the other way that you can look at this is if you want to create a big change in the momentum. Okay? So if you want to create a big change in your momentum, okay? So if you think about this, you have three ways to change your momentum vectors in your car, okay? Your gas pedal makes the momentum vectors bigger. Your brake decreases the size of the momentum vectors. And your steering wheel changes the direction of your momentum vectors, okay? So if you look at driving your car in terms of momentum, you have three ways that you alter that momentum. Make it bigger, make it smaller, change the direction of that momentum vector. Okay? So if you want to create a big change in the momentum, okay, you're in your car and you go, wow, I want to create a big change in your momentum. So if you want this to be big, if you look at a force time graph, like Ismail said, oh, hey, the area of this is going to be your change in your momentum. So if you want a big change in your momentum, you want a big force acting over a long period of time. Because when you have a big force acting over a long period of time, that creates this maximum area. So what that would mean is that if you're driving your car, okay, and you want to create a big change in your momentum, you're going to press down on the gas pedal and you're going to hold it there for a long time because that's going to create a big force acting over a long period of time. Okay? There you go. So, as you go through these problems, you have to focus on what you're holding constant and what you're changing. Okay? So, if you're going to keep the change in the momentum the same, okay, that means the longer that takes to happen, the less force there is. Now, this is where this all comes full circle, right? So we said that force times time equals change in momentum. Okay? That's what we just said. And we said that change in momentum is mass times change in velocity, which is mass times v minus v naught. So here's the deal. So if I divide this by time, okay? So if I divide this by time, then I have force equals mass times v minus v naught over time. Now, since the very first day you were all in this class, and I introduced the units of acceleration, I said the simplest way to calculate acceleration is v minus v naught over time. So oddly enough, all this is F equals ma. Okay, literally, it all just goes back to the idea that force equals mass times acceleration. So, and this should make sense. If you're driving your car and you barely hit the brakes and you come to a stop, oh, that's a small acceleration, which doesn't require much force. If you slam on the brakes, that's a big acceleration, which is going to require more force. Okay? So, if you go back to the problem with the truck, okay? So if you look at the fact that the truck was moving at, where was we at? Okay, so if you go way back up here to the top, and you had a mass of 10 kilograms, 5 meters per second, and it took, and we're going to bring this to 0, okay? Here was our change in our momentum. So if we want to calculate the force, okay, then if you look at this in terms of force times time equals change in momentum. So our change in momentum was negative 50 Newton seconds. And if that took 2 seconds, that's negative 25 newtons. Well, which is the exact same slope of this line. So if I take my change in momentum, which is what's going to happen in terms of this graph, okay, from this point to this point, and I divide it by that time, I get my force. So if I did this in 1 second, it's the exact same change in my momentum, but now I would divide by 1 second, and I would have a force of negative 50 newtons. So you have to focus on what you're holding constant and what you're changing. Okay, so here's the deal. So I've already sent out the lecture notes and the assignment for today. If you want me to print this stuff out, I need to know today, and then I will email you once I get that ready to go in the office, which is going to be this afternoon. Probably, well, actually I'll have it ready to go tomorrow. The assignment I've already sent out. Even if you can't print it out, if you just want to look at it on your computer, that's fine, because you're going to answer all of these questions on another sheet of paper anyway. So you actually don't have to print out this assignment, because you're not going to send it back to me anyway. So if you just want to look at the problems and answer them that way, that's cool, because you don't actually have to print it out. But if you want copies of everything for this momentum, I need to know as soon as possible. If you want to retake that test, again, just let me know when you're ready to take the test, and then I will send that out to you just whenever you want to retake that test. I'll just send you the PDF file with that. Now, because now we're kind of into this routine. So here's what's going to happen. You have this momentum assignment that I'm giving you today. As usual, tomorrow we're going to go over the assignment. I am going to grow absolutely less and less tolerant of you all handing in late work. I have better things to do with my time. Because if this was like in a normal class, you all would have to hand in your assignment at the end of the day anyway. Okay, like at the end of the class period. That's when you would physically have to hand this in. So, I really want these assignments on the day that they are due. And I'm not talking like 9 o'clock at night. Like I haven't figured out a time yet. Well, I'm still working that, but I'm thinking like by like 4 o'clock. That's going to be like my cutoff deadline. I'm still going to play with that a little bit. But, because this is just basically like class. You all are here every day. We're going to go over the assignments. You have a designated amount of time to work on. Okay, time is up. Let me know about that stuff. I'm going to send out the order forms for the clothing. It's pretty cool. And like I said, I'd be honored if you all, if you want to buy clothing, or if you just want to make a donation to get to so you could have like that class panel, that would be pretty amazing. So anyway, peace out, stay safe, and I will talk to you all tomorrow.
See you later.
See you, Sproles.
Good for him.
Bye, Caden.